In this video, we are going to write molecular ionic and net ionic equations for single and double replacement reactions. And then we will look at single replacement reactions to determine what is oxidized and what is reduced. A molecular equation, whether it's a single replacement or double replacement reaction, is just the regular balanced chemical equation. The ionic equation is a little bit more realistic in terms of what the ionic compounds look like in solution. Soluble ionic compounds dissociate or break apart into ions. Notice that the precipitate does not. So here's the precipitate in the molecular, the precipitate in the ionic equation. These ions have actually found each other and made a precipitate that's not soluble in water. But all the other aqueous substances have been broken apart into ions. The net ionic equation is really the heart of the reaction, the two ions that come together to make the precipitate. Here's the precipitate again. We can get from the ionic equation to the net ionic equation by removing the spectator ions. Spectator ions are ions that do not participate in the reaction. They are spectators. They're in solution before the reaction starts, like this potassium ion, and they're in solution after the reaction, like this potassium ion. Nitrate ion here before and after. So if we look at our equation, we see potassium ions on the left side and on the right side. They look identical on both sides of the equation. Nitrate ions on the left side and the right side. Once you get rid of those spectator ions, what you have left are the things that go into the net ionic equation, the two ions that make the precipitate. So let's write the molecular ionic and net ionic equations for this reaction. Remember, the molecular equation is just the regular balanced chemical equation. Here's our molecular equation, our regular balanced chemical equation. Notice how I have the precipitate labeled, the aluminum carbonate, and then my other product is soluble in aqueous solution. In the ionic equation, everything that's soluble in water is actually ions floating around in the water. So we will dissociate or break apart each ionic compound that is soluble. So that's anything that's labeled aqueous. So for the aluminum nitrate, we're going to break that apart into aluminum ions and nitrate ions. Don't break apart the polyatomic ions. Remember, those are covalently bonded and they will continue to be bonded together in water. Put in the charges, and then don't forget to balance. So in our balanced chemical equation, there are 2 aluminums, and then there are 6 nitrates. 2 times 3 is 6. So we're going to turn all of that into a coefficient of 6. Then label each ion with a little AQ. Do the same thing for the potassium carbonate. Break apart the potassium carbonate into potassium ions and carbonate ions with the charges, and then make sure it's balanced. There are 3 times 2 or 6 potassiums, and then there are 3 carbonates. And then each ion gets a little AQ. Now for the products. The precipitate is not soluble in water. That's why it's a precipitate. And so we're not going to dissociate this or break it apart. So we will just recopy what we see in the equation above. But the other product, the potassium nitrate, is soluble. So we will break apart the potassium nitrate into ions. Potassium ions and nitrate ions. Give a little AQ. And don't forget to balance. 6 potassium ions and 6 nitrate ions. So that's our ionic equation. Now let's get rid of the spectator ions. The ions that are there before and after the reaction. They will appear identical on both sides of the equation. We've got potassium ions, 6 of them. And we've got nitrate ions, 6 of those as well. What we have left makes up the net ionic equation. Just recopy. If you've done everything correctly, you should see the 2 ions that are required to combine together to make the precipitate. We're also going to write molecular, ionic, and net ionic equations for single replacement reactions. Remember, the molecular equation, again, is just the regular balanced chemical equation. So now for the ionic equation, again, any ionic compound that is soluble in water, so anything that's labeled aqueous, will be dissociated or broken apart into ions. But the copper metal and the silver metal are just elements, and we're just going to leave them. We're just going to recopy them. The ionic compounds we're going to break apart into ions. So for the silver nitrate, there are silver ions and nitrate ions. There are 2 of each. Give them their little AQs. And then for the copper nitrate, there are copper ions and nitrate ions. There are 2 of those nitrate ions, so my subscript I'm going to write as a coefficient. Give them their little AQs as well. Now for spectator ions, we have only 1. It's the nitrate. That's the only thing that's identical on both sides of the equation. On the left side we have a silver ion, and on the right side we have a silver atom. Those are 2 different things. Same thing for copper. So what we have left, we just recopy as our ionic equation. So a copper atom turns into a copper ion, and a silver ion turns into a silver atom. How do they do this? Through the movement of electrons. And when electrons are gained or lost, we can talk about substances being reduced or oxidized. So this copper that goes from an atom to an ion with a +2 charge has actually lost 2 electrons. Anything that loses electrons we say is oxidized. The silver ion becomes a silver atom, and it does that by gaining electrons because silver has a +1 charge. It gains electrons, so we say that it is reduced. So we'll always have one reactant that is oxidized and one reactant that is reduced in our single replacement reaction. We just need to be able to look at what gains electrons and what loses electrons. There's a little acronym here that can help you remember. LEO for loses electrons is oxidized, and GER for gains electrons is reduced.